the understanding of a new concept related to Newton's laws of motion, and that is the concept of inertial versus non-inertial reference frames, and how to deal with application of Newton's second law when we we are in what is called a non-inertial reference frame. So we'll firstly understand the definition of what is called a inertial reference frame. So what is basically a reference frame? So it is a coordinate frame or system with reference to which the motion of a body or a particle is measured. So you can visualize a reference frame as a system of axes. So some point is defined as the origin, and with respect to that point, an x-axis and a y-axis is drawn. So this is a reference frame. Now, different reference frames can be in motion with respect to each other. So a reference frame which is attached to the ground or the earth's surface becomes what we call the ground reference frame, and in a sense it is absolute because it is at rest with respect to the ground. But different reference frames may not be at rest with respect to ground, they might be in motion. Okay. So the ground frame can be thought of as a absolute reference frame. Okay. Whereas any other frame can be in motion with respect to the ground frame. So for example, if we have a situation where we have an observer who's stationary on the ground, and we have another observer who is inside a vehicle which is in motion with respect to the ground. So in this example, if observer E is stationary on the ground, then the reference frame attached to E is the ground frame. But since the observer B is in motion with respect to A, the reference frame attached to B is moving with respect to the ground frame. Okay. So if there is a reference frame attached to B, this becomes a moving frame, whereas the reference frame attached to A is the fixed ground frame. So just make a note of this part. Then we will understand the definition of inertial and non-inertial frames. So just make a note down up to this part, please. Okay, so now the most important definition: what is an inertial frame versus what is a non-inertial frame? So listen to this portion very carefully. So an inertial frame is one which is either fixed with respect to ground, that is, it is the ground frame itself, or it is moving, but it is moving without acceleration, that is, it is moving with uniform velocity with respect to ground. Okay. So an inertial frame can be of the fixed ground frame, of course. It can also be a moving frame, but if it is moving, it should be moving with zero acceleration, that is, it should be moving with only uniform velocity with respect to the ground frame. So a reference frame fixed to the ground or moving uniformly, that is, moving with zero acceleration. Zero acceleration with respect to this is called an inertial frame. So therefore non-inertial frame is the opposite of this, so it should be moving with acceleration with respect to ground. So it is an accelerated motion, that is, its acceleration is not equal to zero with respect to the ground. So let us understand this with an example or two. Okay. So this is what is happening here. E is an observer fixed to the ground. B is the observer inside an elevator moving vertically with a uniform velocity with respect to ground. Now the simple thing is, suppose a ball is dropped inside the elevator, okay, in free fall. What is the ball's acceleration with respect to A's frame, and what is the ball's acceleration with respect to B's frame, and what type of frames, are each of A and B's reference frames. Okay, so just note down the definition of inertial frame and non-inertial frame and tell me the answer of this question. Yes, that is correct, Aman. Okay, so here what will happen is that as this ball is in free fall, it will be falling with an acceleration equal to g. So whether we are in A's frame, okay, we take x and y axis like this, the acceleration of the ball will be equal to minus gj cap, okay, where g might be 9.8 meters per second square. Or we are in B's frame. When we are in B's frame also, it is the same. It is minus gj cap, because both of them are inertial frames. Both are inertial frames because once we've just seen that it is moving with uniform velocity. No? The observer inside the elevator that is moving with uniform velocity. So its acceleration is zero. So as per the definition of inertial frame, we have seen that B is the reference frame attached to B is an inertial frame because it is moving with uniform velocity or zero acceleration with respect to the ground. Now, as opposed to this, if we were to have a situation where suppose we had an elevator which was descending with respect to the ground at 2 meters per second square. Now, inside this elevator, we have an object which is in free fall. So now B is an observer inside an elevator descending at acceleration this much with respect to ground. Now particle P is in free fall inside the elevator. Once again, find P's acceleration with respect to A's frame. Okay. Take the value of G as 9.8 and again find P's acceleration with respect to B's frame and again state what type of frame is A's frame and B's frame. Yes, Aman, that's correct. But only thing is, A and B should be interchanged. Part A and B should be interchanged for you. Yes, Tantresh, your answers are correct. So basically, here what will happen is that the particle P is in free fall. So that basically means that in the ground frame, that is E's frame, it has a free fall acceleration equal to g downwards. Okay. So in E's frame, with respect to E's frame, the acceleration of the particle will become this much. Okay. But B, the acceleration of the particle will become g minus downwards. And that is happening over here because E's frame is the inertial ground frame, but B's frame is a non-inertial frame because it is accelerated with respect to ground. Okay, so far we haven't talked anything about the application of Newton's laws, how that is affected by reference frame being inertial versus non-inertial. We're just looking at the definition of what is inertial frame and what is non-inertial frame. Yes, that is correct. So reference frame is all about the measurement of motion with respect to one observer's coordinate frame. So observer A's coordinate frame is fixed to the ground. So with respect to his coordinate frame, what will he measure the acceleration of the falling particle to be? He'll measure it to be 9.8 downwards. But observer B's own reference frame his coordinate frame is going down at 2 meters per second square. So he will not measure the falling ball to be coming down at 9.8. He will measure it to be coming down at 7.8 because he himself is going down at 2. His own reference frame is in descent at the acceleration of 2 meters per second square. Okay. Now we come to the part of main interest to us. Application of Newton's second law in a non-inertial frame. From now on, we will use the short form NIF for non-inertial frame, and pseudo force. We'll give that a short form FPS. Okay. So let us understand this in detail. Then, of course, we'll come to pseudo force. So, body of mass m in a non-inertial frame, okay, accelerated at a naught, let's say, okay, with respect to ground, okay, experiences a force called pseudo force due to the frame's acceleration. Now, before we get into the formula and mathematical expression of this force, let us understand this force with a couple of examples. So, one very easy, relatable example is that people standing inside a bus or even an object placed on the floor of the bus, if the bus suddenly accelerates forward, their bodies experience a force backwards. They tend to get pushed backwards. Persons, okay, or a block or object inside a bus accelerating forwards tend to experience a backward force, or they are jerked backwards. So this force here, this is an example of pseudo force. So make a note of this. Now similarly, if you are in a situation where this moving bus, it brakes sharply, it means it tends to decelerate. So the bus moving in this direction but brakes. Okay. Then the people inside the bus will tend to be jerked forwards. Their bodies will experience this type of force. Okay, so this thing. So whenever we think of non-inertial frame and the phenomena of pseudo force that acts on any object or any body inside the frame, the two simple examples you can relate with are these ones: that you are sitting inside a car or a bus, which is initially at rest or even moving with uniform velocity, but the moment it accelerates forward, your body experiences a backward push. Or if it brakes while moving forward, your body tends to get jerked forward or experiences a forward force. So these two are the most natural, everyday, relatable examples of pseudo force. Okay. Of course, there are so many other examples of this. The what your body experiences when you are in a roller coaster is also an example of pseudo force. Okay. What your body experiences when you step into a lift and the lift, let's say, accelerates upwards. Now, you feel heavier for the time it's accelerating. You feel you're pushed against the ground. Or if the lift is going down with acceleration, you tend to feel bit of butterflies in your stomach because you tend to feel lighter. Your body tends to feel lighter than its true weight. So that is because of the pseudo force that is acting upwards. So these are all everyday examples of pseudo force. So again, a person inside a lift that is accelerating downwards will tend to feel lighter than his true weight because there will be a pseudo force acting on his body upwards. So the person inside a elevator, okay, descending with acceleration, tends to feel lighter. So this tendency to feel lighter happens because of pseudo force acting upwards against gravity or opposite gravity. So this is another example of pseudo force. So now, having understood all these examples, we will come to the exact formula of pseudo force. So pseudo force is dependent on the acceleration of the non-inertial frame. Okay. So magnitude of pseudo force is directly proportional to magnitude of this acceleration, and direction is opposite. Okay. And secondly, depends on the mass of the body. So the magnitude of pseudo force is directly proportional to the mass of the body. So with this idea now, we understand that pseudo force is given by a formula which as a vector equation is this, or you can say that the magnitude of the pseudo force is this, and direction opposite. Okay. So this definition is the important one which we'll be applying. Okay, so let us understand the application of pseudo force with an example. So we have the same example of the elevator, which is this time, let's say, ascending. Now inside the elevator, we have a box suspended from the ceiling. So a block of mass m equal to 50 kg is suspended with a light inextensible thread inside an elevator ascending at uniform acceleration with respect to ground. Take g equal to 10 meters per second square. So first part, make the block's free body diagram with respect to observer A's frame, okay, and calculate the tension T in the thread. Again, make the block free body diagram, but with respect to B's frame, and find out the tension. Okay, try this out, people. The moment you make the free body diagram, okay, be sure to incorporate the concept of pseudo force that we've discussed if you are in the non-inertial frame, and you will see that that will give you the correct result as far as tension is concerned. Okay, Aman, your answer is correct. Nobody else has worked it out. Only one person has sent me the answers till now. Please calculate the value of tension for each of the parts that you're getting and send it to me. Okay, so let us understand the free body diagram in each part. So as far as the observer A is concerned, that is what kind of frame? Inertial frame, because it's basically the ground frame. So by definition, a reference frame fixed to the ground is an inertial frame. So in that frame, the body itself has an upward acceleration of 2 meters per second square. Whereas there are two forces acting on the body, and they are the force of tension acting upwards and gravity acting downwards. So observer A being fixed to ground is an inertial frame, and in A's frame, the block has a vertical acceleration of A. So he will write that T minus mg is equal to ma. So T minus 50 into 10 is equal to 50 into 2. So according to him, the tension should be 600 newtons. Okay. So take this down and now make a similar situation, but make the FBD in B's frame. And see what's happening over there. So in B's frame, what is happening? First of all, B's frame is fixed to the elevator, accelerated vertically. So therefore, B's frame is a non-inertial frame, and in B's frame, the block is at rest. So this is the non-inertial frame that is attached to the elevator. So this frame itself is going upwards at an acceleration of a naught. So when we talk about the block, the first force we should talk about is the pseudo force. Then of course there are the forces of tension and weight. So these are the forces in this frame. Okay. So that is the concept of pseudo force. So what we are seeing here is by incorporating pseudo force for the free body diagram in a non-inertial frame, okay, we correctly adjust, okay, balance of forces. So So when we apply Newton's second law with the correct adjustment in the non-inertial frame, it should give the same result that we have got in the inertial frame, because the inertial frame is the absolute frame. So it should not happen that in the non-inertial frame we are getting some different value of tension compared to what we are getting in the inertial frame. Then our analysis would be wrong. Because obviously Newton's second law, whatever it's giving in the inertial frame, is the correct value of tension. So to get the same correct value of tension in the second case, we have to adjust for the fact that we are in a non-inertial frame by incorporating pseudo force. So that is the purpose of pseudo force. It adjusts the balance of forces properly when we are in the non-inertial frame. Yes, free body diagram will differ because in non-inertial frame you have to incorporate pseudo force. In inertial frame there is no pseudo force. And pseudo force is always opposite to the acceleration of the frame. So in this case the acceleration of the frame is vertically upwards. So the pseudo force acting on it is downwards. Okay. So let's look at another example of non-inertial frame and the incorporation of pseudo force. So this time we will consider the reference frame being horizontally accelerated, like the example of the bus that we talked about. So this is a fixed seat on the bus. Bus is having a horizontal acceleration in this direction, 5 meters per second square. Now what we are doing is we are placing so a block 10 kg mass is placed on a seat fixed inside. So make the free body diagram for the block. in A's frame. Okay, just try this out next. So you'll see the block is in contact with two surfaces. The horizontal surface of the seat, which will be applying a normal reaction vertically upwards, and also the backrest of the seat or the vertical surface of the seat. The block is in contact with that also, and that will be pushing the block with a horizontal normal reaction. So to calculate both the normal reactions, the normal reaction applied by the horizontal surface of the seat as well as the vertical surface. Yes, Tantrish, that's correct. Anybody else got the answer? So first of all, when you are considering the free body diagram in A's frame, so A's frame is inertial, and with respect to A, the block has horizontal acceleration 5 meters per second square. So according to this observer A, who is an inertial frame, the block itself is having horizontal acceleration, and the forces acting on it are one normal reaction like this, another normal reaction like this, and wait minutes. So N1 is the horizontal normal reaction applied by the backrest of the seat. N2 is the vertical normal reaction by the seat. So along the x-axis, so these are the forces, and this is the analysis of the free body diagram in A's frame. Now, Okay, so what the observer B will be concluding that because of his own horizontal acceleration, so the reference frame is non-inertial with a horizontal acceleration of a naught, like this. So the block being at rest in this reference frame. So there's a pseudo force which is actually pushing the block back. The direction of pseudo force should be opposite to the direction of acceleration. And this is what causes the block to be pushed against the backrest. And the backrest has to apply an equal and opposite normal reaction. So this normal reaction N1 is because of the pseudo force pushing the block against the backrest. And this normal reaction N2 is because of gravity pulling the block down. So it's pushing against, whereas the block itself is at rest. So along the x-axis, what is happening is that N1 is balancing the pseudo force. Net force is zero. And along the y-axis, N2 is balancing weight. So ultimately, the conclusion is the same. Whether you are looking in the ground frame or you're looking in the non-inertial frame, you will say that there are two normal reactions acting. The backrest is applying 15 newtons, and the horizontal surface is applying a vertical normal reaction of 100 newtons. But you can understand why the concept of pseudo force becomes important, because without pseudo force, we cannot analyze the free body diagram correctly in the non-inertial frame. So once again, you are seeing that very important point that the analysis by Newton's second law in a non-inertial frame is correct only when proper adjustment of pseudo force is made. If we had not made the adjustment of pseudo force here, then our conclusion would have been that N1 is zero, because the block is at rest, so there should be no horizontal force. But only because we have adjusted properly with the pseudo force, we are understanding how N1 is occurring. So let us understand with one final example, which is now going to incorporate the concept of a moving body inside a non-inertial frame. So far, we have seen examples where The free body diagram we were making was of a body which was at rest with respect to the moving frame. But now we can always have a situation where inside the non-inertial frame, the body in question is actually in motion. So let us see an example like that. So what we have is a smooth inclined plane inside an accelerated reference frame. So this is a smooth inclined plane, theta equal to 37 degrees. But this itself is inside a vehicle which is having this much space. Okay. Now what we are doing is, so a block of mass 2 kg is released from rest on an inclined plane fixed inside a horizontally accelerated vehicle. So make a free body diagram of the block in the vehicle's frame and calculate the acceleration of the block as seen from inside the vehicle, okay, or simply with respect to the vehicle's frame. Okay, so take down the question first, then we'll discuss. So you can see here that this observer who is inside, he himself is becoming the non-inertial frame, and he is seeing the body accelerating down the inclined plane with an acceleration e. So e is the acceleration of the block with respect to an observer inside the vehicle. So that becomes the non-inertial frame fixed to the vehicle. So this is an acceleration down the inclined plane. Okay. So this is what we have to calculate, and now it becomes very easy because all we have to do is we have to understand that we are in a non-inertial frame that is having a horizontal acceleration like this. Okay, and in that frame, the forces acting on this body are pseudo force m a naught in magnitude, opposite in direction, gravitational force, and normal reaction. So this angle will become theta. This angle is theta. And in this frame, the body is having a downward acceleration. A like this. So when we show the same forces in resolved form, so mg's components, so these are mg's components which I have shown. Okay. Then pseudo forces components. Pseudo forces components I have shown. And normal reaction I don't need to resolve because it's already along my y-axis. And in this frame now, the body has an acceleration down the inclined plane of E. So we take this as a x-axis, this as a y-axis. So along the x-axis, we have the equation ma naught cos theta plus mg sin theta is equal to m. So theta was 37 degrees, g is 10 meters per second square. And along the y-axis, this is our equation. Right. So as you can see in this question, it is not going to be possible for us to analyze the motion in the ground frame directly, because we don't know the direction of acceleration with respect to ground frame. But in the non-inertial frame, we know the direction of acceleration. See, what is happening is, if you consider a ground frame observer, so consider a person on the ground over here, what he will be seeing? He will be seeing that the body was here, and after some time, it's moved like this. After some time, t plus delta t is moved like this. So he doesn't even know the direction in which the body is moving. So in the ground frame, the acceleration is not at theta, because theta is this angle to the horizontal. Okay. The acceleration is along a direction which is like this sort of direction. This is the direction of displacement. So that's why it's not really going to be feasible to make the free body diagram in the ground frame. Here it is going to be feasible to solve only in the non-inertial frame. Okay, so that is the importance of pseudo force and non-inertial frame. It is for situations like this where it is not possible to analyze directly in the ground frame how the motion is. Because the motion is very specific with respect to a moving frame. So in situations like this, the application of pseudo force becomes very important, because we don't have the option that can we make the FBD in the ground frame or can we make it in non-inertial frame. We only have the option of making the free body diagram in the non-inertial frame. So we have to do that with the correct adjustment of the non-inertial frame, which is the adjustment made by incorporating pseudo force into our free body diagram. Okay. So hope with this example you have understood the full application of non-inertial frame concept and pseudo force in a non-inertial frame. So with this, you should be able to solve most of the questions of H.C. Verma's Newton's laws of motion exercise this week. So next week we will keep some time aside for doing questions from H.C. Verma, as well as seeing some additional things in Newton's laws, including a couple of more methods of constraint relation for system of pulleys that we discussed earlier. But mostly we are done with the essential concepts of Newton's laws of motion. We will take a couple of more lectures, including next week and then next week, to complete problems and some more problem solving techniques. So that's it for today's class, people. Wish you all the best, and make sure you prepare properly for the test coming up on Sunday. Prepare up to today's lecture, okay? But pseudo force concept will not be there in the test, so just prepare up to free body diagram and simple pulley systems and things like that, inclined plane, simple pulleys, those type of problems.